Welcome. So we are starting a new chapter today. The chapter is ray optics and optical instruments. This is chapter 9. This is actually second part of the books. In the 12th standard, you have NCERT has given two books. This is the first chapter in the second book. Okay, so we are going to basically talk about what is uh, the ray optics and optical instruments. Now, the optics we have been actually studying from quite some time already. Okay, we have been studying optics for a very long time. Even when we were in 10th standard, when we were in 9th standard, 8th standard, everywhere we have kind of studied optics. Okay. However, in all those places we have given a very nicely qualitative approach to optics, in the sense that we understood the properties of light. We know what is reflection, what is refraction, what is dispersion. All that qualitatively we have understood, in the sense that we know that if this happens, this happens. When light goes from a rarer medium to denser medium, how it bends. When light travels through a prism, it splits into colors. All that we have studied. Okay, and even the image formation, basically for lenses and curved mirrors like concave mirror, all that we have. When the object is in between C and F, where will be the image? All these things we have already done. Okay, so however, in this session what we are doing is, so we are going to basically in 12th standard we are going to get deeper into physics, okay, of light. So to go there, before that we will actually kind of concretize our understanding of where we stand in terms of what we call ray optics. Okay, so then we will go into wave optics and we look at basically electromagnetic wave theories and all that. Okay, radiation, dual nature of light, all that we will study. So the first step is to basically just go back and look at what we have done and develop some quantitative methods on that. Okay, develop some proofs, like let us say we have taken some formula for granted. Now let's go and actually try to prove that formula. Those kinds of things we are going to do in this chapter. Now the first statement that I am going to make is, the light travels in a straight line. This we have learned from, let us say, 5th standard. Light travels in a straight line. But is this true? It's a question. Is this really true? Does light travel in a straight line? Now we're going to question that. So we realize, we'll get into some kind of experiments here and realize that it is not necessarily true. However, it is just an approximation of the travel of the path of light. Okay, it's light. The light actually behaves like a wave. When it behaves like a wave, it goes like a wave. It need not be a straight line. But wavelength is basically very small, and hence we see for all practical purposes that it goes in a straight line. So in ray optics we take that stand. We take light as a ray. Okay, and it has or a beam. A beam means a set of rays we call beam. Okay, light beam or light rays are what we consider in ray optics. With that in mind, we will basically do all our work. Okay. However, that is not the exact truth, in the sense that it is not 100% true that light travels in a straight line. It is to be taken for all practical purposes that it is a straight line. Okay. So now what we will do is, we will just go with that assumption that it is a straight line. Okay, and then we will get into understanding the properties of light based on that, which we already know. We are going to just state those properties. Light reflects. We know the reflection properties. So if we take, for example, a mirror, and if a light falls on the mirror, when I write like this, that means the top part of the, I am just keeping the mirror like this. The top part of the mirror is polished, nice surface. This side is basically covered. Okay, so when light falls on this, it reflects. So the laws that get followed because of that are what we call laws of reflection, which you have studied always. Angle of incidence is equal to angle of reflection. Okay, that is one law. In fact, the first law is the incident ray, the reflected ray, and the normal drawn to the surface, all three lie on the same plane. Okay, that is the first law. Second law is these two are equal. Okay. So this is basically is experimented. We have seen that it happens. So this law is more from the experience. Okay, these two are the laws of reflection. Okay, so first is about on the same plane. What are the three things? These three things are on the same plane. Incident ray, reflected ray, and the normal. All of three are on the same plane. It is not like it is coming here and reflecting this way. So they are all the same plane. Okay. And second law was I is equal to R. Angle I is equal to angle R. So I will go ahead by mentioning here two important mistakes that people generally make. Two mistakes. One, in the mistake of stating a law. Second, in the mistake of understanding a law. There are two mistakes people make. So just point it out and move forward. So the mistakes are generally what happens is we say incident ray, reflected ray and normal are on the same plane. First law, fine. Second law, people say okay, incident ray is equal to reflected ray. That is not true. Incident ray is different from reflected ray. Okay. So they are not equal. They are the rays. So what are equal? It is the angles that are equal. Incident angle and reflected angle. So this is called angle of incidence. This is angle of reflection. So those two are equal. So please state it properly. Always angle of incidence is equal to angle of reflection. Incident ray is equal to reflected ray is wrong. Okay. Now, second important problem is in the case of a nice mirror, okay, this kind of a rule is applied. Suppose if we have an irregular surface, instead of a mirror like this, I have a rough wall. Rough wall, I will write it as something like this. It's a rough wall. On the rough wall, the light when it reflects, one light ray may go here, another light ray may go here, another may go here like this. It's called irregular reflection. So this is called regular reflection. All light rays actually nicely follow this parallel, regular reflection. So somehow we think that in the case of a regular reflection, the laws of reflection are followed. And in the case of irregular reflection, the laws of reflection are not followed. And that is again a wrong conclusion. Okay, laws of reflection, that doesn't care about the kind of surfaces. On all surfaces, laws of reflection hold good. In the sense that it is just that the surface being with a different angle. Okay, so let us say if you take only this particular line, okay, you can see, and when you draw a perpendicular to that angle, so for that perpendicular, these two angles are equal. In the sense that if I write it a little more, I will write like this. I'll just expand the surface, zoom it up. Okay, and when the light falls on this, okay, it actually, how does it go? It actually goes like the same formula, same rule. Angle of incidence is equal to angle of reflection. This is I and this is R. It is because of this that the light has gone somewhere else rather than going in the expected path. Okay, it is because of the roughness of the surface But even on that small rough surface, the law is followed. Okay. The law is everywhere followed. If the light falls on this part of the surface, like this, now you draw a perpendicular to that surface, and then light goes like this. So it looks irregular reflections because of the surface being not smooth, and it has nothing to do with laws of reflection not getting followed. So remember that laws of reflection is always followed, even on a curved surface. Whenever I talk about a mirror, okay, let us say I have a mirror like this. So let us say this is my concave mirror. So if the light comes from here, let us say, where does it go? If you ask, it still follows the laws of reflection. What I am going to do is, wherever the point at which the light is hitting, there I draw a tangent. I draw a tangent, and to that tangent I am going to draw a perpendicular, and that perpendicular is the normal. First, always you have to draw the normal. Then we look at, this is angle of incidence. Angle of incidence is always with respect to the normal, and angle of reflection. Now, if you draw, this is R. So this is how it reflects. Again, it follows. So the light always follows the laws of reflection, whether it is an irregular surface or whether it is a surface which is curved everywhere. That's important. Okay. Second important point. So now we have talked about basically two misunderstandings which I have clarified. And another important point is that whenever light actually goes from, let us say, one medium to the other medium, like I have a glass slab. This is my glass slab. Okay. If the light actually goes from, the light falls on this, really what happens is, because it is a glass slab, okay, the light enters this, and when it enters, it bends. So refraction happens. We know that. But when refraction happens, reflection also happens. Some part of the light actually goes inside, and some part of the light reflects. So the part of the light that reflects will actually follow the laws of reflection only. So this is equal to this. The part that goes through refraction, that follows the laws of refraction, that we will discuss later. So that is basically a few things about reflection. Now, with this in mind, let's go and start directly onto curved mirrors and derive some formulas that we already know of. Okay. So what we will do is, when you look at a mirror, concave mirror, so we talked about it, we actually done a lot of work on the concave mirror in our 8th, 9th, 10th days. Okay. So a concave mirror is one in which this side is, let's say, rough, and it reflects on this side. Okay. We have also learned that we can actually write down here the middle of this point, what we call, we are going to call this as pole or P, and we also know that this is principal axis, or we can say x axis. We know that. Okay. And we also know that if you actually take, let us say, some kind of a radius of this curve. Okay, if this is the curve, and if you basically complete the circle, okay, and that circle has a center, let us say here. So that center is called as center of curvature. So if you take a compass and keep it at one point here and the other point here and draw like this, that's when you get the correct curvature, okay. That is the center of curvature. And we have also found out, we used to use that there is a point here called F, principal focus. Okay, and we said that basically the value of from distance to this one, we called it as focal length, and distance to this point, we called it as radius of curvature. These are some of the terms that we are already familiar with. And we also have certain very interesting, certain very important sign conventions. So we generally go wrong in sign conventions. Okay, that is whenever you actually the questions that you need to answer in these areas of mirrors and lenses, they are all very easy actually. Substitution into some kind of a equation, but people do it wrongly because of sign conventions. So they neglect the sign conventions. So there is a habit. Okay, almost everybody neglects sign conventions, and whoever neglects, they definitely will get 0 marks on those questions. Okay, so it is known, and it has been established. So please listen to the sign conventions properly. Okay, there are only 3 sign conventions. This is very easy to remember. Okay, what are those sign conventions? Let us write down sign conventions. Okay, so first of all, okay, first sign convention, all distances have to be measured from pole for mirrors and optical center for lenses. So for lenses we call it as optical center, for the mirror we call it as pole. So these sign conventions are same for both mirrors and lenses, just 3 of them, remember. Okay. The second one, so what does it mean? First one, actually what does it mean? That means measuring the distances in one direction. See, generally we know distance as, when you say CF or CP, when you say it is some length is what actually we call distance. And distances we never measure to be positive or negative. Okay, only in displacements we talk about like that. But in this case only in the case of lens and mirrors, for some obscure reasons, okay, people have figured out that you have to actually measure distances using their direction. It has some direction. Distances have some direction. Okay, the reason is very obvious actually, we'll come to know. So in the sense that if there is something here, some distance FP I want to measure. So if you are measuring from F to P, it is one direction. If you are measuring from P to F, this is another direction. They are different. Remember that. That's all. Okay, and we are saying that whenever we measure distances, we always measure from the pole. If you go this side or that side, whichever side you go, we measure from the pole along that axis. Okay, that is the distance we measure. So that is what we are saying. In the case of lens, optical center. Okay, and second important rule is that the distances that are measured, the distances that are measured in the direction of incident ray are positive. That means in the opposite to the incident ray are negative. That's all the meaning of that. So one which is measured in the direction. So incident ray, let us say assume that is object is somewhere here. Object is somewhere here, and incident ray is coming in this way. Incident ray. This is our incident ray. So if this is our incident ray, if I want to measure distances in this direction, negative. In this direction, if I measure, it is negative distances because you are going opposite. In this direction, if you measure, positive distances. Okay. Then, lastly, heights above x-axis are positive. That means whenever you want to measure heights, you measure from this axis. So if you are measuring this direction, this is positive height. If you are measuring this direction, this is negative height. Correct? So this all are the rules. That's all are the rules of the game. 3 simple rules. So once you know these 3 rules, we will not make any mistake. So the next step that I am going to do is certain assumptions basically while using the ray diagrams. Some important assumptions while using the ray diagrams. First important assumption is we have to understand this concept of parallel rays and paraxial rays. Okay, parallel rays. Paraxial rays. And parallel paraxial rays. These 3 concepts we have to understand. Okay. So otherwise we will always think that there is some mistake going on here. Okay. So first of all, when you have a lens or a mirror, okay, I'll write here a lens in this case, okay, or a mirror also you can write. So in this case, if I get, this is my principal axis, okay, if I get any ray parallel to principal axis, any ray, okay, so they are parallel to principal axis rays, okay. However, these rays are parallel to each other. Okay. So if the rays are parallel to each other, they are called parallel rays. That's all. In the sense that it is not necessary that it has to be parallel to the principal axis. When I say parallel rays, it means that it can be like this, or it can be like this. So they are also parallel. Okay, so whenever we talk about parallel rays, the meaning of parallel rays is that the rays are parallel to each other. That is all. Okay. Now the first step is that. Next is, what is paraxial rays? So paraxial rays means this. Now if I have a lens here or a mirror, whichever one, okay, and if the rays are actually falling very near to the optical center or pole, in the sense that somewhere in this region, it's all coming only in this region, only in this region. You see this from here, some very near to optical center, not too far away, not to the edge, rays which are coming very near to this, and they make very small angles to the axis, like it can be like this. So there are two rules. Rules 1, very near to pole or C, okay, depending on whether it is mirror or lens. Sorry, not C, O, pole or optical center. Second rule is small angles with x-axis. Okay, if these two rules are true, such rays are called paraxial rays. Okay, so they need not be parallel to each other. Paraxial rays need not be. It can be like one ray like this, another ray like this, whatever. These are all called paraxial rays. The rays which are very near to, falling very near to C or O, up or down, even here, but also small angles with the angle that it makes here, this theta, that is very small. It creates very small angles, theta. Okay. So such rays are called paraxial rays. Okay. Now, if you actually mix these two, that means rays which are parallel to each other and are also paraxial. So such rays are actually called as parallel paraxial rays. So example to that is for example this and these two. These two rays are both parallel and paraxial. Okay, and let us say these two rays are also like that. These two rays are also like that. Okay. This and this are not. These two rays taken together are paraxial. These two rays taken together are paraxial. These two are paraxial. Okay. This and this, if you take, they are axial, but they are not parallel. Okay. So if you understand this much, then all the other things will fall in place. This is basically what we are going to do here is all the ray optics rules that we use for mirrors and for lenses and all, when we talk about writing the ray diagrams, and all the formula that we use, all of them are true for paraxial rays only. The formulas are not true if a ray falls at an edge like this with some obscure angle. Same rules are not true. All your image formation rules, everything, formula 1 by f is equal to 1 by v plus 1 by u, all of them, they aren't true, okay, otherwise. Okay. So remember that they have to be paraxial rays. Now, the next step that we are going to do is, we have actually always taken this as true. So our focal length, what is a focal length? So let's define focal length first. What is a focal length? Focal length actually, okay, is the point at which image will get formed if the rays are paraxial ones. So if you get a paraxial rays, okay, in the sense that if you actually take a mirror and send some paraxial rays like this, for example, two rays, it forms an image at f. They can be parallel. Yeah, they can be parallel. What we are talking about is parallel paraxial rays. Parallel paraxial rays form or focus at a point called focal point or principal focus. So whenever you have a parallel paraxial ray, see I have written a parallel paraxial rays, it will come into principal. So this whole, it comes at a point, okay, when you say point, it is actually the plane. So it forms in a plane here. It's called a focal plane. It is never just a point, okay. If it is parallel to the axis, principal axis, then it will come to one point here. But if you make it slightly different angle, it will come a little down here, okay, and if you put it that side, it will go somewhere up here. So ultimately it is actually going to form an image, or it will focus, that point focuses on a focal plane, and the distance to that focal plane from the P here, we call it as focal length, okay. Focal length is a distance to that focal plane. So if you are asked to basically define what is a principal focus, then it is whenever a parallel paraxial rays form on a mirror, okay, concave mirror, they focus onto a point called as a principal focus. The distance to that point from the pole is basically focal length. Now question basically is that focal length will be actually is equal to r by 2, that is center of curvature, radius of curvature divided by 2. That we have used a long many times before. So let's prove that. So it's very straightforward to prove it, okay. So I'm going to basically draw some pictures, okay. Let's say I will use the same drawing to do that, okay. So I'll put, how do I generally do image formation? Let's say first image formation, how to do. So let's understand the image formation first. So to do image formation, so how to find out where is the image? The way to do is from all the points of the object, infinite points of the object, you take rays, okay, and see where they go and converge. That's where the image will be, in the sense that ideally what we need to do is from point, let us say this is my object AB, from point B you take one line, one ray, because light comes like that, one ray, and see where it goes, and from the same point B you take one more ray, okay. It is sending light in all directions, anywhere, all directions, all the rays you take, and they will go and hit it. When they go and hit the mirror, they reflect. When they reflect, what do? They follow the rules of reflection, which is simply angle of incidence is equal to angle of reflection. When you do that, they will all finally come and focus and join at one point. All these rays will come and join at one point, if at all, if they do it. Then we say that point is the image. Let us say if it went here, came back here, let us say, and this fellow went there somewhere, came back here, this like that, if you draw all of them. So finally let us say they all kind of formed here, B dash, one point, okay. If such a point, okay, let me just make it more clear here. If this is B dash, if such a point comes where all these rays go and reflect and join, and such a point is called the image of point B. So to get one image, or to get an image of one point, we used umpteen number of lines and use the law of reflection and get back here. So next you have to do is one more point, let us say here, next point, and from there you get another umpteen number of lines, and all of them you find come back, and somewhere here it will come. Focus. So like that you keep doing all the points, and you will get all the points of the image. That is exactly how it happens in reality. But we will actually make a lot of shortcuts to do this. What are the shortcuts? How to make it work with shortcuts? Instead of taking so many points, we are going to take only 2 points, A and B, 2 endpoints, and then later we will join. Okay. If A gives here, comes here, and B comes here, we will join and say this is the object image, A dash B dash. Okay. So first shortcut we do is, instead of taking so many points from the object, we take only 2 points. And then second shortcut we do is, we don't take so many rays. We take only 2 rays, or maximum 3 rays. Okay. So we take only 2 or 3 rays. So what kind of rays we take? So we have some technique to do that, where we don't have to keep on measuring angle of incidence and angle of reflection and drawing the normal. All that we can avoid if we take these 4 kind of rays. I will show you there are 4 kinds of rays we can take. Okay, rays to be considered for image formation. 1. Okay. Out of these 4, any 2 you can take. Okay, 1. Okay. Ray parallel to principal axis. The first ray. You can take a ray which is parallel to principal axis. Any ray that is parallel to principal axis, when it reflects, it goes through the principal focus, like this. Like this. Any ray that is parallel to principal axis will go through the principal focus, like this. So if you actually draw this line from C, okay, to this point, let us say this point is M, then definitely the angle of incidence and the angle of reflection, okay, these two will be same. If this is theta, this also will be theta. Okay. So angle of incidence is equal to angle of reflection. Now I will not write this one. So this is first rule. Second rule is, ray, incident ray that passes through F, incident ray that passes through F, what happens to that? Such rays generally, they reflect parallel. See, if you get a ray like this, they will actually reflect parallel. So they will come back parallel. So if you send parallel, they come through F. If you send direct through F, it will come parallel. So this is again following the same rules of reflection if you carefully do it, but this is easy to do. Okay. And then third, so ray parallel to principal axis, okay, reflects through F. Ray that passes through F reflects parallel to principal axis. So ray that passes through ray that passes through C, ray that passes through C, that means suppose if I can draw, now I cannot draw here. Suppose if I can draw, okay, suppose if I am far here, I could draw through C. Okay. So through C, if any ray goes, now it is hitting the mirror at right angles, because C is center and this is a circle. Center to circle, if you draw a radius, it is right angle to the tangent. So hence it reflects back, because I is 0, it reflects back onto the same line. If it goes via C, any light ray, it comes back via C again, reflects back on the same line, reflects back on the same line. And lastly, a ray that hits P reflects with the same angle. What does it mean? If I actually draw here, I keep erasing this just to make sure that it is clear to you. So this is actually our original first ray. Okay. Now, if one more ray, if I take it through directly to P, from here to here, P, straight line I have to write, to directly to P. That reflects with the same angle, like this. That reflects with the same angle. This angle and this angle are same. So these are the 4 rules. Okay. So in any of these 4 rays, we can take it and form image. In this case, I have taken ray number 1 and ray number 4. Okay, ray number 1 and ray number 4. Okay, so I have taken, this is the one going like this, ray number 4. Those two are joining here. I will call this point as B dash and this point as A dash, like this. Okay, so what I am going to now do is use this picture to prove F is equal to R by 2. You don't need that much of an elaborate picture, but yes, you can do it using that too. Okay, F is equal to R by 2. So what is this angle? This line, if you see this line, this line is the normal. If this line is the normal is always C, in the radius of curve, radius is normal to tangent. So radius is the normal. Okay, this line is normal. So this is basically incident ray, that is, let us say theta. Okay. So if this is theta, okay, this is also theta, correct? So together these two are 2 theta. So look at this line, BM line and AP line are parallel. BM and AP are parallel. So this is basically cutting both the lines. So this angle and this angle have to be equal. So this is 2 theta. And since this line is cutting these 2 lines, this angle and this angle has to be equal. This is theta. Okay, now what I am going to do is, I am going to draw a perpendicular here and call this D. okay, because I want to get a right angle triangle. I will now write down, okay, tan theta. Tan theta is equal to how much? MD divided by CD. I will also write tan 2 theta, which is equal to MD by FD. Here I am using quickly the fact that we are using paraxial lines. All the lines are supposed to be paraxial lines. So, paraxial lines means what? They make very less angles with the principal axis. So, theta, so though it is shown here as big angles, okay, in reality they are making very less angles because we are taking small rays which are coming very near to this. Okay. So, paraxial angles, hence because of paraxial rays, because since rays are paraxial, theta and 2 theta are very small. Therefore, tan theta will tend to theta and tan 2 theta will tend to 2 theta. This is basically our you have learned in the last year. Tan theta will tend to theta when theta is very small. Okay. So, in this case then it becomes theta is equal to MD by CD and 2 theta is equal to MD by FD. So, we will write here 2 into theta will substitute from here MD by CD is equal to MD by FD. So, MD gets cancelled. Okay. Now, I will say that CD will be approximately equal to CP because it is a very again paraxial. This is very near to this and this is very near to this. Because of the paraxial, okay, CD approximately equals to CP and FD approximately equals to FP. Okay. But when you talk about CP, that is nothing but R and FP is nothing but F. Okay, so we can write it as 2 into 2 divided by 2 into 1 by CD. CD is CP with R is equal to 1 by F, which we can say is means F is equal to R by 2. So, this is the proof. So, you can prove geometrically why F is equal to R by 2. So, you may be asked to do this in some test or exam and it is quite easy to do it. Okay, now we have to now do the mirror equation. Okay, mirror equation solution. So, we always know, we already know what is mirror equation. We have done it in the earlier classes. So, we talked about basically 1 by F is equal to 1 by V plus 1 by U. So, we need to basically prove this. This is called a mirror equation. So, if we can prove this, so then we can actually use this later to solve some problems and see where are the difficulties, what are the complex problems that can come. So, all that we can see in the next session. Thank you.